All right, so this last video is going to focus on reaction mechanisms. Reaction mechanisms attempt to explain the series of steps that a reaction has to undergo, or the reactants have to undergo in order to form products. These help us to see the intermediates, substances that are formed in one step and then used in a subsequent step, as well as how catalysts are used in a chemical reaction, how they get consumed and then reformed. There are reactions that can occur in a single step, and those mechanisms would just be written based on that reaction, and you could write its rate law without doing any experimental collection of data. You can write it based on the stoichiometry of that reaction. In most reactions, however, there are a series of steps that the reactants have to undergo, or the intermediates have to undergo to form the products. And all the steps up to and including the rate determining step, the one that runs the slowest, are going to be combined together to determine the reaction's rate. So this is an elementary reaction, which means that we can write the rate law from its stoichiometry. We do not need to have any experimental data. We see that ozone and oxygen atoms are combined to make two oxygen molecules. And so the rate law would just be the rate times, or rate equals K times the concentration of ozone times the concentration of your oxygen atoms. Here, however, this reaction would require multiple steps. The first step is the slowest of the three, and then the two after it go more quickly. You have HOOH combining with iodide ions to make HOI and hydroxide. Then you have the HOI combining with iodide again to form iodine and hydroxide ions. And then the two hydroxide ions combine with two hydronium ions to make four waters. So to write the rate law expected for this mechanism, we take a look to see if the reactants that are present in the slow step, are they consumed in subsequent steps? Are they made again, or sorry, the reactants that are consumed in the first step, are they made in subsequent steps? If that is the case, then they would not be included in your mechanism. But these two reactants are not found on the product side of our reaction. So our rate law would just be based on the concentration of the slow step, HOOH, and I minus. If the slow step had been switched with the first fast step, and you had had HOI plus I minus forming I2 and OH minus first, and then you had the HOOH combining with the I minus, you would have seen that you would have, I'm taking a look to see, one of the HOIs would have canceled out, but you would have been left with the HOOH and the two I minuses. So the slow step is a summation of what has taken place up to and including that slow step. So for our purposes, it was the first step, pretty straightforward. Just kind of keep that in mind in the future. The overall balanced equation is just combining these three individual steps together. So this is like Hess's law in the sense that if a reactant is found on the product side, its concentration would cancel out. But if you find it in more than one reactant or more than one product for the equations, you would add them together. So our balanced equation would cancel out the HOI. It would also combine together the OHs, and the I minuses would be added, and we would get HOOH and two I minuses along with two H3O pluses, forming I2 and four H2Os. Our intermediate for this reaction would be the HOI because it was made in the slow step and then consumed again in the first fast step. And we did not have any catalyst because we did not have any of the opposite, where we had a reactant be consumed and then reformed in a subsequent step. I left out OH, I'm sorry. OH would also be an intermediate. Hydroxide is an intermediate in this particular mechanism because it is made in the slow and the first fast step, but then they are both used in the last fast step. So what would a reaction coordinate graph look like for this mechanism? Sorry, I forgot that I was going to need to include that piece. Let me see if I can get my drawing tools up. Go back for a second. So if I was going to draw this reaction, this is really bad, sorry about that. All right, the first step would have been much taller than the second two steps. I didn't tell you whether this was an endothermic or exothermic reaction, so depending on whether it was endothermic or exothermic would depend on whether the energy of the reactants would end up lower or higher than the energy of the products, but this would be your slow step, the one that had the most activation energy. This would have been your first high step. And again, this is just a rough sketch. And then this would have been your second high step. So sorry for the bad drawing, but I hope this helps.